Hi everyone, this video is going to go over a couple notes about problem number 6. So problem number 6 asks us to look back at 1 through 5 and see if we see any connections specifically between the force diagram and the description of the motion. So if I zoom out, I'm in a document that has my solutions for problems 1 through 5 so that we can see what we notice as we walk through them. So if I look back, I'll try to move slowly so I don't make you dizzy. If I look back at problem 1, we'll see we have this force diagram with two arrows, one up, one down, and we have congruency marks to show that the magnitude of those two forces are the same. For the motion of this, I've added an image. The motion was that the cart was still. So there was constant velocity, but that velocity was 0. For our second one, we have this force diagram you'll see on the right. We have two different sets of congruent forces. So we have the up and down arrows of equal magnitude, and then the left and right arrows of equal magnitude. Again, we had a situation, as you can see from this photo, where there was constant velocity and the cart was still. So we have two cases of constant velocity. In our third problem, we have, again, this force diagram you'll see on the right. And in this case, we have two congruent arrows, the up and down arrow, and then we have one arrow to the right. This does not have a matched pair. And we'll notice in this case, we had motion where there was increasing velocity to the right. So changing velocity, not constant. So we have this one arrow to the right without a matched pair, and we have increasing velocity. In our fourth problem, you'll see the force diagram to the right has two arrows that are congruent, the up and down arrows, and then it has two more arrows, but they're not congruent. We don't have congruency marks on them. We have a bigger arrow to the right in my case and a smaller arrow to the left. Maybe yours are reversed depending on your setup for this problem. The key was that the two people are pulling with different forces. So one arrow is bigger than the other. And with one arrow being bigger, we have increasing velocity in the direction of whichever side your bigger arrow is on. So non-constant velocity. And in the last one, number 5 right here in green, we have an arrow up and an arrow down, and we had constant velocity. So notice this concept of net force is key. Net force is basically like saying the sum of the forces. So when we have congruent arrows in opposite directions, if you think about adding those up, it's like they cancel each other out, and we have a net force of 0. We also say that this means that the forces are balanced. We have one up, we have one down, they're balanced with each other. In all the cases where the forces are balanced, we have constant velocity. The cart may be moving or not moving, but the point is that the velocity is constant. In the situation where we have a net force where the forces aren't balanced, such as example 4, notice that if we were to add up these forces, while the up and the down arrows balance each other, the left and the right don't, and there's a net force, an overall force to the right. And whenever there's a net force that's greater than 0, that means that the motion is not constant. So we have an increasing or decreasing velocity. So let's just make a note and summarize that down here for problem 6. The key being that if we have balanced forces, or net force of 0, then we have a constant velocity. And if we have a net force that's not zero, then we have non-constant velocity. So maybe that's speeding up or slowing down.